Hello everybody, this is Paul Ramond from the past for you. I hope everybody is having a good time watching this LISA presentation. First of all, I would like to thank the organizers for the flawless organization even during these uncertain times of COVID-19. I would like to present to you today one of the works I've been doing during my PhD in France, along with Alexandre Tiec and Camille Noûs. So this work talks about the first law of mechanics, which a few of you may know. This is basically an equation that is involved in the theory of binary systems of compact objects. And in this talk, I would like to present how we approach the problem of deriving the first law, and what is the first law of mechanics. And at the end, I would like to present to you a few preliminary results we have, and how it can be used and how it has been used in the past by people to make good physics with it. So let me start with a brief reminder about the first law of mechanics, for those of you that don't know about it. So we are here dealing with binary systems of compact objects, so be it black holes and or neutron stars, pick the one you prefer. And when we talk about the dynamics of such a system, usually it involves many physical parameters, among which we can distinguish what I call the bodies properties. For instance, here the mass and the spin of the bodies, for instance. And other types of quantities which are more global, which we could call the binary properties, in the sense that it describes the binary as a whole, as a system of many objects, here too. And this could be, for instance, the binding energy or the orbital frequency of the binary. And basically, the first law of mechanics is a simple algebraic relation or differential equation, depends, between those bodies properties and the binary properties. So what we seek here is a simple equation between the binding energy, the angular momentum of the binary, in terms of the mass, the spins, and other physical parameters of the individual bodies. So first, let me give you an example of such a first law. This example has been derived for a few years now by Alexandre Tiec and collaborators in 2012. And it involves a binary system made of two bodies, two black holes or two neutron stars, or one black hole and one neutron star, with mass m1 and m2 and orbital frequency omega. And this equation simply reads like this. So this is a variation equation from which you can derive a system of PDEs, for instance. And as you can see, this equation has on the left, as I said, global quantities, or the binary quantity, the binding energy E, the orbital frequency, and the angular momentum J. And on the right, you have more local or individual properties of each body, which are, in this case, the masses, m1 and m2, and some coefficients in front of those masses, which are called the redshift, and which are of high importance in this type of works. So the first law, as it has been derived by Le Tiec and collaborators in 2012, only accounts for one simple description of the system. That is what we call the monopolar order description, which is simply a set of two point masses, orbiting around each other. We can go beyond this. We can do better by considering the dipolar order, and a first law has been derived at dipolar order by Luc Blanchet and collaborators. And this simply amounts to including a spin, extra degrees of freedom to each body, namely the spin here. And finally, what is the main focus of our work, is to go one step beyond, that is the quadrupolar order, and include not only the mass and the spin, but also the deformations, potential deformations of each body. As you know that these bodies can be drastically deformed, especially at the end of their rotation. So more on this later on. So how do we derive such a first laws between global and individual properties? Well, one way that we have tackled the problem for now, which seemed to work, is to consider the restricted case of circular orbits. So as you know, there can be many general orbits, like eccentric ones and precessing ones between two compact objects. But you may also know that because of the emission of gravitational waves, actually the orbit circularizes itself quite rapidly. And so it is not completely useless to study this type of orbits, in particular because we can use circular orbits in a sequence to construct arbitrarily complex orbits using different mathematical techniques, which I won't go into. So if we consider only the circular orbit, a perfect circular orbit, and we look at the space-time diagram associated to this system of two, let's say, black holes here, then we see that there are two helices, which basically is the translation of having a circular orbit that evolves with time. And so this helical trajectory, in fact, is encoded mathematically and rigorously in the what we call a helical symmetry. So this is basically considering a space-time with a symmetry, which is in this case is helical. And you may know from fundamental theorems in mathematical physics that when you have a symmetry somewhere in your space-time, then you have a conserved quantity. So mathematically, we describe this helical symmetry by a Killing vector. Here I call it K. And associated to this Killing vector, there is what we call a Noûs charge Q, which is a conserved quantity in our space-time. It turns out that this conserved quantity Q is in fact related to the global quantities associated to our binary system. The global quantities for instance, the binding energy or the orbital frequency or the angular momentum, total angular momentum of the binary. So this is the first step in a way in our work. And the second step is simply how do we model such compact objects, which may be, for black holes, they are pretty simple objects, but for neutron stars, they can be arbitrarily complicated, depending on their thermodynamical properties, the equation of state, pressure field, velocity field inside the neutron star, and so on. And so what we choose to do is to, in fact, look at the body from far away. And this is what we call a gravitational skeletons. So in particular, if you look at the space-time diagram of your neutron stars, for instance, here, you have, in the 2+1 diagram, you have a world tube. And this world tube, if you look at it from far away, then it becomes simply a world line. And this world line, which I call gamma here, will be the support, the mathematical support of a simplification of the complete energy momentum tensor, TAB here, which encompasses all the thermodynamical quantities of the neutron stars. Instead of this complete energy momentum tensor, we consider some kind of Taylor expansion of this tensor around the world line gamma. So for instance, here on the bottom left, you have an example of such Taylor expansion. I won't go into the details of the equation itself, but you can see that it's some kind of expansion over the different derivatives of some terms which are called monopole, dipole, quadrupole, and so on. So basically the takeaway here is, the takeaway result is that we model the compact object, which may be very complicated, by a few of its intrinsic properties, such as the mass, the spins, and the deformations, and all of these are included as some kind of Taylor expansion, which we call a gravitational skeleton. Skeleton because at the end of the process only remains the bones and the general structure of the neutron star and not its fine details, such as flesh and nerves that the skeleton lacks. So this is the second step, and of course the third step is to relate the first two. So in other words, we need to link the geometry of our helically symmetric spacetime to the skeletonized version of the energy momentum tensor, and relating geometry to energy momentum in GR usually relies on the Einstein equation, because that's all we have, basically, that's all we need. And so you can derive some equations that relate those two quantities You have an example here by work by Ayer and Walt. And the type of equation you obtain is, once again, I won't go into the details of equations, but here is the type of equation you obtain. As you can see on the left, you have the neutral charge, which we talked about, the conserved physical quantity associated to our symmetry. And on the right, you have the gravitational skeleton and the killing vector, and also the metric tensor on the far right. So basically, the complicated part of our work is to insert into this very equation the skeleton expansion, the Taylor expansion if you want, in place of t, and then compute these very complicated integrals. And if you manage to do that, then you get the first law of mechanics up to the order at which you have truncated your Taylor expansion. So on the left, you will obtain the binding energy and global quantities, and on the right, the mass, spins, and quadrupolar deformations all come from the integrals over the stress energy tensor. And in other words, you can see that this kind of equation is quite similar to the one on the bottom, except that there is a lot of work to do by passing from one to the other. So this is the main idea behind our approach, and so far it has been quite useful. So we have classified our results in three different topics, let's say. The first one is to ensure that from the point of view of the mathematics of the helical symmetry, everything is well behaved for the physical system. And so what we have first shown is that imposing the symmetry, the helical symmetry, indeed ensures that each particle follows a helical trajectory. In other words, the quadrivelocity of the particles is tangent to the killing vector. And in the other hand, we have shown that each multipole of the particles, so mass, spin, and so on, are quantities that are Lie dragged along each of these helices. So this is especially useful and simplifies a lot the dynamical equations, the equations of evolution and equation of precession and so on. So the second result we have at the moment is that we indeed recover all the found results, namely the first law at monopolar order with the mass, the one I showed you, and the one at dipolar order with the spins, at least in linear order of spins for us. And this coincides with the literature on the first law of mechanics. So at least our method works for the first and second order. And we have preliminary results for now at the quadrupolar order. And what we have done is we have decided to describe the quadrupole of each of our particles, or black holes, by two types of effects, one of which is the spin-induced quadrupole, simply because when a body is spinning, it tends to flatten at the poles, and one that is tidally induced because of the tidal forces between the two bodies. So this is a work in progress. And one final note, maybe, before I end this presentation, how it is used. Well, first of all, let me mention that this kind of work doesn't care about the mass ratio between the two bodies. It's general enough to account for supermassive black holes binaries and also for extreme mass ratios. And what we can do with it is many things, among which comparing different approximation schemes in GR is one of the main and most useful things to do. And it can also be used to calibrate the potentials in the effective one-body models, which are used to build the gravitational wave templates. And also, if we get to the quadruple order, we start to look into the constraints on the equation of state of the neutron star, with a typo in my slide. Sorry for that. So this is what we can do. Hopefully all of this is clear. Don't hesitate to contact me. My mail address is below my picture. And I thank you for your attention. Thank you for watching at least. And hope you have a great LISA experience this year. Bye.